My name is Tony Fast. Is this working? Yeah, okay. And I'm a developer at Continuum Analytics. I work as a data scientist, and a lot of what I want to do is get data on the page in a meaningful way. And I've been working a lot with bokeh, and bokeh kind of gives me some really interesting interactions and expressions that I can do visually with data. One of the examples that I'm going to show, just because I think it's really pretty, is playing with color, playing with alphas, and playing with different kinds of zooming and color features of bokeh while I'm moving around in a plot and exploring it. Gives me some really rich color, some really rich interaction, and it's a little bit novel compared to most of the JavaScript libraries that I've used before. So I've been working at Continuum, and I've been exposed to a new tool set. And it's really curious to think about going back to your old work with a new tool set. So I come from material science, and I've worked in manufacturing for a very long time. And one of the things that we do is we look at microscope images. And on the screen right now are 12 different microscope images of alpha beta titanium. Titanium is a heavily used product in manufacturing, and the processing, or the way it's heated, the way that it's rolled, the way that it's made has a really big impact on how the material not only looks, where each of these images come from different experiments, different processing techniques, but also has a big effect on how it performs. Now, the microscopist took 120, 130 of these pictures, so they realistically can't go through and explore all of these. So using some data science methods and using bokeh, we can create a really rich visualization that actually gives a very strong image comparison of these images. So we have 12 different processing steps which give all of these different feature structures of the images. We do a little bit of statistics to create a reduced embedding of them. And then I get down to a projection of all of the data. And what we're looking at here is each color is actually a experimental method or processing method for making this piece of titanium. The processing method that you use makes different kinds of titanium. If you use a different processing method, you get a different kind. So we want to explore these images really well. Each point here is a reduced embedding of a microscope image. And it's reduced to a XY projection. But each of these points actually represents a picture. And I want my microscopists and my manufacturers to be able to realize that. So the ability, using the zoom features and adding some alpha fading to this, actually allows me to zoom in, and the nearness of the pictures and the overlapping of the pictures actually tells me something very similar about them, or different about them, depending upon how they're moving from each other. So at this point here, we can see that this is from heat treatment 27, which is what HT indicates. Same thing here. So zooming in, we can see the images that are responsible for those embeddings. This notebook's available online. I put it on my Twitter. It's DocFast. It's the first link there. This notebook runs on NB Viewer. All of this is available on the client using some bokeh and using some JavaScript and using Jupyter. You're able to present a really rich client-side application that's data-backed on the web. That's shareable by a link.
I'm Leland McInnes. Can everyone hear? Yep, good. Okay. From the Tutt Institute for Mathematics and Computing in Canada, and I'm interested in clustering, and I'm interested in just exploratory data analysis, and that has slightly different needs on clustering. So, first rule of data science is look at your data, because real data is messy, and you're probably wrong about it, and there's probably some outliers that are screwing you up. So, look at your data. Second rule of data science, no, really look at your data because you're probably wrong. You know, you probably have some people who are, subject matter experts who know all about the data, and they're going to tell you things about the data that they know are true. Those are almost certainly false, as a rule. That's what I've found whenever I've dealt with this. So really, look at your data. So that's great. How do I look at my data? Well, there are a million different things you can do. Visualization's a good start, but depending on what data you've got, there's all kinds of different ways you can go about getting some sense of what's going on in your data to try and understand it better. So out of all of those, I'm going to focus on clustering. So what should we use for clustering? Well, obviously, k-means. No! All right, so this is my rant part. Never use k-means for exploratory data analysis. There are places where k-means make sense. I'm not personally sure where they are, but I'm sure they exist. But for starters, k-means is not a clustering algorithm. It's a partitioning algorithm. It partitions your data. It doesn't assign things to clusters. It assigns everything to some cluster. So even if you've got noise, you've got outliers, you've got random corrupt data points, they're going to get assigned to your clusters whether you want them there or not. And that means when you go and look at your data with k-means clusters, you're going to be wrong because it's going to have mess in your cluster that's going to screw up all your intuitions about what's going on. K-means also assumes that your data is going to cluster into nice Gaussian balls. Now, that's probably true if you do the right transformation on your data to get it in the right form. But if you can do that, you're probably already done because you understand your data really well. So that's probably not the case. And choosing the number of clusters for k-means, that's a lot harder than you think. Real data's messy, and yeah, there are cluster goodness measures, but they're diverse and often wrong. So there's really no good way to get a handle on what the number should actually be, other than, kind of guessing. So what do we need from clustering for exploratory data analysis? Well, the first thing is don't be wrong. I don't care if you don't get everything right. I don't care if you say, I don't know. Just don't lie to me, because that will ruin my intuitions, and then I'm going to misunderstand the data from there on in. So I want something that's going to be conservative and try and give me as close as it can to the right answer, and just say I don't know in whatever places it can't work things out. It's got to have as few parameters as possible, and those have got to be intuitive parameters that I can just guess without having to do a whole bunch of exploratory data analysis to work out what my parameters should be. Clusterings have to be stable. I don't want it, when I rerun it, I don't want to get a completely different clustering. If I resample my data, I don't want a completely different clustering. If I tweak my parameters a bit, I don't expect that to give me a completely different clustering. And we need performance and scaling to large data sets. So if not k-means, then what? So what am I proposing? Well, dbScan is a perfectly good algorithm that meets a lot of these criteria. It's already an sklearn, so that's great. It's very, very fast, and it clusters instead of partitioning. It's a little hard to pick the parameters for it, but it's something. Robust single linkage is a better option if you're interested in the cluster hierarchy. It's a version of single linkage that's robust to outliers. If you've never heard of it, look into it. There's some links there, write them down quickly. It's a great way to go. And you can get really quite good performance depending on the implementation. And the third option that I'm going to suggest is HDBScan, which is kind of like robust single linkage with an extra step that pulls out a flat clustering. So the end result is very similar to dbScan, but you're down to just one fairly easy to choose parameter, really. So that's all I have, and hopefully that's informative. Thanks.
My name is Adam. I am a second-year grad student at Yale University. And I signed up mostly for the adrenaline, but also to give you like a summary of 2 years of my data science in the wild. I'm going to talk about depression. Depression is an extraordinarily important issue. Over 300 million globally have depression, and it's really expensive to treat, right? Workplace costs, it's a really expensive issue. Workplace costs associated with people leaving work for depression cost $52 billion per year in the United States alone. The question of what we do about it is the problem at the moment. There's two main approaches. One of them is to use drugs called antidepressants, but the efficacy of these drugs is notoriously low. Between 11 and 30% of people actually get better when they take these drugs, even after 8 to 12 months of treatment. But it's okay, right? We have loads of different antidepressants, so if it doesn't work, you should just try another one. Sounds like a joke, but that's actually what we do, and it works for most people eventually. In theory, that's not such a bad problem, but the problem is that people reach the correct antidepressant through a completely trial and error process. It would be really nice if they didn't have to go through this treatment by treatment sequential selection problem, and we just had a way of estimating before they take a drug whether they were going to get better or not. I'm going to skip through some stuff because these are old slides. So the data that we have is taken from an old clinical trial called STAR-D. It's the largest ever clinical trial of depression, and they enrolled 4,000 people. The only point that you need to know about this trial is that all 4,000 people started out on the same drug. It's a common antidepressant called citalopram. And because this trial has already finished, we know the outcomes for this trial, right? So 4,000 people went through this. They all took the same drug, and our outcomes are pretty easy to label. Basically, the green people are people who, after 12 weeks of treatment, were no longer depressed. So this is kind of like the clinical objective. And so what data do we have to predict these outcomes? I went through the trial and extracted all the information that was collected about these patients that was available at baseline. It included things like demographics, diagnostic questions, and a load of questions, questionnaires that they filled out about their symptoms. The problem here is that now we actually kind of have too much data for a simple model. We need some way of constraining this problem. Most of you will probably be familiar with this. We used a method called elastic net regularization. This was a cross-validated model, and we basically threw everything in and then ranked the absolute beta weights to take the top 25. We now use the top 25. We now use those top 25 features. Oh my God. Sorry about this. It's kind of painful. We now use the top 25 features to train a gradient boosting algorithm, but generally it doesn't make a difference which model you use. And the questions that were identified by this process were generally meaningful. It was things like baseline depressive severity, their current employment status, and a couple of specific symptoms that they experienced. Like I said, sorry, we trained a gradient boosting model to try and predict these outcomes using the baseline information. And statistically, it worked. We end up with sensitivity and PPV in the order of 63, 64%. You have to bear in mind that at baseline, we only expect 11 to 30% of these patients to remit. So if our model thinks they're going to remit, they now have between a 2 and 6 times greater chance of remitting. The model performance is probably best considered against the performance of actual clinicians. So we got a sample of practicing psychiatrists that did their residency at Yale to predict treatment outcomes using the same data. You can see this was the distribution of responses that we got. The dotted line in the middle was chance performance. Obviously, most of the clinicians below that. And the model that we built was in the top right-hand corner, which was the same as the best performing clinician. I mean, we trained the model on 4,000 patients, right? So it's not super surprising. So in any case, we think that we have a model, and it's kind of better than clinicians. We then wanted to we need some kind of confidence that the model generalizes. So we went and got an independent clinical trial that was run 6 years later. It's a little bit smaller. They only enrolled 665 patients, and they were spread across 3 treatments, kind of give us an interesting opportunity to test the model on some other samples. The model did have above chance accuracy when we tested it on a similar antidepressant. It also worked when that antidepressant was combined with a different antidepressant, but it did not work in a third treatment arm where patients took a combination treatment of 2 different classes of drugs. I'm going to skip all of this. The take-home message from that is that you don't have to predict whether they got better. You can predict specific symptom changes as well. So the take-home message is that I'm trying to convince people in the clinical world that statistical models might help guide medication choice in depression. We're now doing some work to try and model changes on specific symptoms rather than the overall outcome. And we're also extending this approach to other mental illnesses. I have some academic acknowledgements, but realistically, the only people that we should be acknowledging are the people who develop these open source data analytic tools, because without them, we wouldn't be able to do this. But thanks a lot, guys.
Okay, so this talk, I have nothing up my sleeves at all. So we start with a CPython built from source. It's 3.5 because Ubuntu doesn't come with 3.5 in the package manager, so I had to build it from source. So all I'm going to do is make install. So I'm going to start with a brand new, unaltered, unmolested Python 3. Now, while this is installing, I will tell you that I tried to do this at PyCon Canada for a 35-minute talk on Saturday. It failed miserably. It was the worst talk I have ever given in my entire life. I was so embarrassed and so ashamed. So hopefully, it'll work better right now. So here what we can see is we have a Python 3, and we have pip. I'm going to pip install a module that's on PyPI. It's called rwatch, and we'll see if this works. Give it a second. OK, it seems to have worked. So now we'll run our Python interpreter. Python 3. Let's see if it, oh, not watch. We just want to do that. OK, and here we have this. It created a module called rwatch. Now, you might wonder what rwatch does. Well, it adds some stuff to the sys module, get rwatch and set rwatch. What do set rwatch and get rwatch do? Well, we'll type help. This gets the target set with sys.set rwatch. That's not very interesting. Let's see what set rwatch does. Set read watches for the specified objects. Well, what on earth is a read watch? Well, some of you may be C developers and may have played around in GDB, and sometimes you find that you don't want to debug some code by putting a breakpoint on a line of code. You want to debug some code by figuring out what's happening to the data. You may have millions of data items being sent into some system, and one of those data items is causing an error. So you want to say, whenever that data item is read, put a breakpoint. That's what a read watch is. And we seem to have been able to add this to Python. So let's take a look and see how this works. Let's create a variable 10. Let's create a watch, just some callback. All it does is print saw this object at this frame. And return the object. We'll set the rwatch for that object and this function. And every time we try and access that variable, it triggers our code. That's kind of interesting. Let's create a function. It takes an x and returns x and x times 2. Let's call it with our x variable that we set a read watch on. Look, it triggers that 3 times. 1 on when you pass it to the function, and twice inside the function itself. So every time you try to access this variable in any way whatsoever, to read it in any way whatsoever, you can hook into that and have some custom code. Well, that's kind of interesting. I wonder what else you could do with that. What if you wrote your watch like this? Nope. Well, that's kind of interesting. Every time, well, I have to reset the watch. Let me reset that watch. And actually, before I do that, let me make just 2 little simple bindings. Now I'll reset the watch. Now, every time I try and access x, I get a runtime error. That's interesting. That's kind of like sandboxing. If I try and access y, y should be, if I try and access the elements in z, which include x, I get nope. And I can't seem to access this variable at all. I can't print it. I can't pass it to a function. I can't read it from a function. I can't do anything with it because the watch just raised an exception. So that's kind of interesting. Read watches can then lead to sandboxing. Well, I wonder what else I could do with this. Well, one interesting thing that you saw was I returned the object. I wonder what kind of interesting stuff I could do if I return something else. Oops, let's do that one more time and get the indentation levels just right. OK. Now, one other thing you may have seen is when I set rwatch, I could pass any mapping. So what if I did this? So now it triggers this watch on everything, on any variable that I give it. So if I give it the number 1, it becomes 2. If I give it the number 2, it becomes 4. Let's make this a little bit. I'll show you because you can't see the side of the screen. So I'll hide that. So you can see 1 becomes 2, 2 becomes 4, 4 becomes 8, 16 becomes 16. X equals, or so 1 plus 1 is now equal to 4. X equals 1. X plus X is now equal to 8. That's kind of weird, and that could probably ruin somebody's day. But if I may have a second more, there's one more kind of neat thing you could do with this. Some of us come from backgrounds where we are originally Java programmers or C programmers or C++ programmers. And one of the first things that we wonder about Python is, what happened to all the pointers? Could we use this to add pointers into Python? Well, maybe we could. And let's give that a try, and then I'll kick myself off the stage. So we have 2 variables, x and y. We have a function that makes a pointer. Now this is a little bit hokey because we have to do some mechanics to make sure that the watch doesn't trigger itself. One thing that you may wonder after I get off the stage is what kind of twisted mind must I have to have come up with this in the first place? Okay, so let's say z and z at is equal to making a pointer on x. Let's set up our watch. Now, every time I access z, that variable redirects me to the variable x. And I can repoint z at y and access that. Yeah, simple pointers in about 6 lines of code. Now, the really interesting thing that I don't have time to get into is how on earth did I do this in an importable module? How do you add this to Python in an importable module? Something that you can pip install on any Python 3.5 as long as it's not on Windows. Think about that, and maybe you can see my talk later in our program. Thank you so much.
All right, so I'm going to talk about a concept called abstract rendering. I don't know if I'm actually speaking into the mic or not. So plotting is good. Plotting helps us understand what our data is doing. It helps us make decisions based just off the plot. You don't necessarily need a computer to do that. You can look at the plot and determine what your data actually looks like. Plotting lots of data is hard. So if I was to take the census data from the 2010 census, that's about 300 million people plus some change, and just plot that with matplotlib, this is approximately what it would look like. So we have a lot of saturation on the East Coast and a lot of white space on the West, or like the Midwest. And that's just because we're plotting the data, we're taking the data point, we're mapping it to a glyph, so a point, and it's oversaturating at each pixel. And so we're not getting a lot of intuition based off this. And if we were actually to change how we're plotting this and plot where we're clipping in black, it looks a little like this. And so you can see all of the black bits are oversaturated, and all of the gray bits are undersaturated, meaning that they were moved to white when they were plotted if you were scaled linearly. So that's not a very informative plot, just plotting like this. And so there has to be some way we can go back to getting intuition, like we normally would when we're plotting a small amount of data, but plotting lots more. And so one solution is abstract rendering. It's a concept that came out of this paper by Joseph Cottom and Peter Wang, and I can't remember the other guy. I apologize to them. But the link is right here. It's from Iowa, or no, Indiana. And so the basic concept is to take the data, move it to an aggregate of some form, and then have that mapped to an image. And so one example would be to take the data points, so each person, count by people that are going to be mapped to that pixel, and then do a log scale by pixel. And we do a log scale based on the Weber-Fechner law. So linear scaling, some kind of intensity, gives to an exponentially visual, so perceptually visual change from white to black, but doing it with an exponential increase in brightness distributes it linearly. And so we can actually get a better perception of what's going on. So if you actually look at this, on the top we have a linear scale, and on the bottom we have an exponential scale, and so you can see the difference. Maybe not on this monitor. Anyway, that is from this phenomenal website right here. It's a great lecture on color, if anyone's interested. And so I have a fun demo, which hopefully will work. Oh boy. Okay. Hopefully this works out as it did on my computer. So this is the census data being plotted using the concept of abstract rendering. So what we're doing here live is we are aggregating by count, as I mentioned, and then taking the log of the data. And so you can actually get a much better visually perceptive understanding of what's going on with this. And so the point I'm trying to get across is that you can still actively plot large amounts of data. You just have to think about how you're doing it. You can't just map directly using matplotlib or some other plotting library. You have to think about how to possibly aggregate the data and still get meaning from it. If I have a little more time, I can show some other fun things. So if we zoom in on New York, this is going to re-render. Cool. So this is all done with Python. The code is unfortunately not open source. Hopefully that gets changed. It gets pushed to GitHub at some point in the future. Cool. So there's New York City. We can actually change the last step there. So we've computed aggregates. We've done count bys. I've actually counted by race. This has got it grouped down into 5 different races, race groupings. So if I do a different final step, we can actually see New York City colored. So blue is white, green is black, red is Asian, orange is Hispanic, and brown is other. And so you can see New York is extremely colorful. Let's see if we zoom in on where we are. Get out a little bit. Let's see, I'm trying to think of other fun things to do. So Detroit. All right. Go out a bit. It's going to take a second. There we go. So that's Detroit. Yep. Let's see, what else could we do here? If I zoom out, let's get the whole map. So this is all running Python code in the background. This is a change from an old Java server. This is now moved to 100%. It's like 400 lines of Python. And should hopefully get put up on GitHub sometime soon. So this is the standard composition. This is saturating. If we were to do a linear scale, so just go from min to max, this is what it would look like. It's almost all just one shade of pink. And if I turn off labels, you can see a tiny red spot for New York. So that's not nearly as useful as doing the log scale. That's about it, unless anyone else wants to see something else that's in my talk. Cool.
My name is Richard Postelnik, and I'm a developer for Continuum Analytics. My background's in financial engineering. So today I'm going to present a demo on calculating credit valuation adjustment using Monte Carlo and Numba. Credit valuation adjustment is a way to price a derivative instrument and account for counterparty default. So this is the likelihood that someone that you have an arrangement for, that the person that bought your product, your credit product, likelihood that they're going to default on the deal that you made together. And before the financial crisis, this wasn't really something that was looked into and is now part of the Basel III requirements that banks have to calculate. Why I'm looking at it here is that calculating CVA on a firm-wide level at a whole bank, banks have millions of credit products. They have thousands of counterparties, each with their own inherent risks. So doing a Monte Carlo simulation of this type, it can become a very big problem to try and calculate. And trying to write this in Python might be a little slow, but let's see how we can write it in Python and get some C speed using Numba. So first I start off by generating random bank data. I'm working with 2 products here. The 2 products I'm going to calculate in the simplified example are foreign exchange and swaps. So here I just generate some random data about the counterparties, their hazard rating, so their likelihood of default, as well as the size of the deals being the credit instruments, the interest rate of the deal, the swap rate for the deal, and whether it's in US dollars or in euros. So this is all done in basic Python here. I'm not doing anything fancy because this is just generating in order to deal with the example. So here we go, and we just generate some NumPy arrays filled with our deals, each one being assigned a random counterparty, randomly assigned their values. This is kind of what a single deal looks like here. It just becomes a bunch of numbers. I've enumerated the types of deals. So this would say this is a foreign exchange product. as opposed to putting in a string right here, because in Numba it gets a little weird with the data types they have to use. So here I enumerate it, makes it a little simpler. Here I generate my random normal curves for doing the Monte Carlo simulation, estimating out the time steps, producing the normal steps that we're going to use to calculate the price of the instruments in each time step. And then here is the whole Monte Carlo function right here. And this is all in pure Python using NumPy. Well, actually, here it's not really using anything. This is just pure Python. It's going to take in an array of the deals, some parameters that we want to pass in, and in Numba, you have to pass in the result if you're going to use this GU vectorized function, which is what I'm using here to compile this to C. In a sense. So the result of this, I ran this in Python. Originally, it took about 10 minutes. This is still a work in process, but when I ran it in Numba, it took about 200 milliseconds. So that's a very big difference. And when I scale, this was only with a couple of thousand deals. In reality, I would want to scale this up to 2 million, a couple million deals, and see how that works. So yeah, so here this says this number, this 0.039, I scaled the number down to say, okay, so about 4% of our total portfolio is likely to be in default. So we're going to lose about 4% of this total value. So I don't want just one number. That doesn't really tell me anything. I want the speed so that I can calculate this number under many initial, or changing my initial conditions and see how that affects my CVA calculation. So here, just to look at the data, the random data that are generated, this kind of shows the breakout of the rating of the counterparties, how they were generated and allocated. You see that there's about 50% with 0 corresponds to A rating and 4 corresponds to E. See here, I want to see what happens with different level of volatility. So going from 0 to 1 and calculating CVA for each one, now I can kind of see how my CVA number will change as I change volatility. Here it's not too interesting because this is a very simplified calculation, so it's a linear relationship. Same thing here. I want to see what happens when I start with a different interest rate. Kind of see a little convexity in the curve here, and glean some information from that. Sorry, it looks like the bottom's cut off, but why we want this is I don't want to just look at one number. I want to look and see how I can go and know how my number will change under different scenarios. And this took me a day to write it in Python using NumPy, Numba, Bokeh. Didn't have to write any JavaScript, no HTML, no C, nothing. And in one day you have a tool that people can use. That's it.
Hey everyone, this is a talk I gave a week ago in Chicago in a high-frequency trading conference, and it is an hour long, and I'm going to compress it to 5 minutes, so it's going to be a bit fast. So basically, what we're going to do is we try and forecast, market prices because money. Now, how are we going to do that? Well, basically, we need to actually see what is a time series. Time series is a trend and noise. Good. Let's continue. Now, what we want to do is just basically forecast the future. Now, how are we going to do that? Well, I'm pretty sure that most of you, if not all of you, is familiar with linear regression. Basically, you get samples, you try and find a line that represents those samples. Now, if you take that and put that on a time series, you won't get good results. So what do? Basically, a good technique is to take the time series and make sequence and then apply your model to that. Now, yeah, we have just done supervised learning, which is not interesting. And actually, it is, because, all right, my last function is RMSE. Good. So what I want to show you is what happened when you do that. Well, you actually get pretty poor results. Now, this is because we didn't take something in consideration. The time series is not stationary. Now, how do you stationary? How do you perform stationarization to a time series? Well, there are many methods, and basically what you do is you transform it somehow. So good, let's transform it somehow with, that transformation. Why is that? I don't have time. Good, let's continue. Now I want to point out something which is, for us humans, that thing might be pretty hard for, having any sort of, prediction of what's going on with that. But, all right, before I put that to the algorithm, I'm going to show you the algorithm full structure. Is you take the time series, transform it, chop it up to sequences, put it in through a learning model, and concat it, reverse the transformation, and you get your prediction. Now, that's the transformation. Now, when you do that with the transformation and without the transformation, you get really better results with the transformation, and we didn't even get to more complicated models. Now, why use linear regression? Why not polynomial regression? Good. Actually, nothing stops us, so let's do so. If you take the same transformation with polynomial regression of, degree 5, you get better results. So why not degree 99? Because of overfitting. Overfitting, really easy. We can pretty see that those samples represent a line, and if we try and use a too complex model to predict those lines, it will come up with something like that, and its prediction of the next sample is going to be here, which is not good if you want to invest your money in that. And I have no time, but actually I got a really good demonstration of a backtesting strategy based on that algorithm, and you can see your money just go down and down and down and down and down. Good, let's continue. So basically how you deal with that, cross-validation, everyone here should be familiar with it. What we did here is we searched for constants that represent our data. Good, so why not take that and go make it, put the function at the end. So this is where you get the perceptron, the artificial neuron. And if you stack them up, you get a neural network. Good, so why only one layer? No reason, let's put more layers and see what happens. All right, so when you train more layers, you can actually see that you get good results. So why only 2 layers when you can have a lot of layers? Well, you cannot have layers forever. All right, if anyone thinks that you can just go like while 1 layers and everything will be all right, it's not going to work that way. Every layer adds a lot of work, of regulation and everything, and so on and so on. But if you take a really deep network, well, there are many, many researches about that, and you can get really good results only by that, without actually having more complex and insane models like I have in the next slides, which I'm not going to talk about. So when you do that, you get even better results. Now, the only thing I want to show you guys, because of time, is what we did here is we took the input and just give it to the network. What happens when we, preprocess it a little bit? Now, the most simple thing we can do with, linear time series, and is just compute the technical analysis indicators and see how that works for our model. And we can see that our model performed really good after that. And the rest of the talk is about how to make it more insane, and every layer does something else, and so on and so on and so on. And I have not a lot of time, so yeah.